the session on hardening your Kubernetes security with active threat detection by Ludovic Toison. Ludovic is head of engineering at NFQ Asia. Yeah, please.
All right, good afternoon, everyone. I'm very glad to be here with you today to share about security aspect, especially in the context of Kubernetes. My name is Ludovic. I am head of engineering at NFQ Asia. We are located in 6 countries: Germany, Poland, Lithuania, Egypt, Thailand, and Vietnam. And our mission is to scale businesses. We are passionate about technology, but of course we like more to build products. And our mission is to support startups and especially companies to build their products, to ship them, and to operate them. And of course, as part of this mission, over the last couple of years, we have been extensively working on the Kubernetes platform, and especially on the security aspect, in order to ship faster and having an improved release time. All right? When we designed the security of a system, usually we can think about the way castles and military construction actually builds. You have these famous pictures of Edinburgh Castle, Scotland. It's a castle that I really like because it's quite impressive. It's built on the top of a rock. You have massive walls. You have a line of defenses. And when you design actually the security of a system, it's pretty similar to the way castles are built. Especially when you implement security, we usually use a combination of 2 principles. Usually we think about prevention. What are the measures we want to implement to have some prevention? The castles, for example, will have walls. He will be top on a rock. You will have defensive measure, which is the prevention. All the measures that you will take to prevent something bad from happening. But of course, in case your preventive measures are not enough, you would like to implement some detection. The ability to be alerted when something bad is happening. Do you have some kind of alarms? Do you have people that are watching? And in case someone managed to break into your defensive measure, you are able to detect and actually react. In Kubernetes, of course, we already have a set of primitives, right? As part of the default platform, you can already implement the preventive measure, like cluster accesses. You can configure the way the deployments are controlled. You can isolate the resources inside the cluster. You can audit what is happening, and you can also isolate the network. But what is happening if something, a processes or someone managed, despite all this measure, to break into your Kubernetes cluster? You would like to be alerted. And today, this is what we are going to explore for the last couple of minutes. Basically, what we would like to do is to detect threats by monitoring the activities that are happening inside the Kubernetes cluster. We would like to be able to monitor what is happening in terms of processes, what is happening in terms of connections, and based on some scenario, detects strange behavior and be able to react, right? Despite you have built all your preventive measure, don't forget that maybe something you have not think about, maybe there is some vulnerabilities, and at the end you would like to be not blind, but to react. And this is the purpose. For example, we would like to monitor what is happening at the container level. We would like to be alerted if, for example, on the production platform, someone managed to execute inside a container and to execute some shell commands, right? On production, it should not happen very frequently. We would like to be alerted as well if a production container suddenly executes a privilege escalation with a sudo command. As well, it's not super usual, and we would like to be alerted. Or if, for example, some sensitive file is tampered, or if some outgoing connection is initiated. All of these scenarios should not happen on a regular basis on production platform. We would like to do the same as well at the cluster level, right? We think about containers running in Kubernetes, but At the cluster level as well, we would like to be able to detect what is happening. If someone is creating, for example, a service account in a technical namespaces, such as SCAP system, not very frequent, normally it should never happen. If, for example, a sensitive file is mounted on the host as well, this is something that is not expected. Or if some strange privilege binding is created, all these scenarios should normally never happen, and we would like to be alerted. Finally, when we know pretty well how our application running on Kubernetes should execute, we would like as well to restrict the context in which they operate. If I am running Elasticsearch, for example, and suddenly I have like an exotic port that is open, for example, 60,000, I would like to be alerted because I know that per default, Elasticsearch has a set of common ports. So it should never happen that suddenly I have an exotic port that is exposed. Or if a process that is executed, Elasticsearch run in Java, if suddenly I have a Python process, something really weird is happening inside my container, I would like to be alerted. The way we can do that is to use a technology called Falco. So there is different solutions, of course. I could use log analysis, right? I log everything that is happening on the system. Pretty low tech, but it can work with like pretty heavy work. We could use as well like Wazoof, which is, for example, a tool to detect a strange pattern in terms of connections. But in the context of Kubernetes, there is already a tool that is kind of like implemented for that, which is called Falco. Falco is a threat detection engine that has been written in Go and C++. It's been initially implemented by SysDic and then had been released to the community and joined the CNCF recently. Okay? So today it's a fully open source project that we can like install on a cluster, we can also contribute, we can have access transparently to the issues log, so it's an open source project. And basically, Falco is able to analyze the activity of what is happening in a Kubernetes cluster at various levels. We can detect what is happening at the container level, at the cluster level, and also at the application level. And this is exactly what we are looking at. The way it works, Falco has an engine in which we will feed a couple of rules, okay? Some rules, some patterns. For example, A, as a Java container, you should not run a PHP or Python process. And based on the input Falco will receive, he will trigger some output behavior. He can execute, for example, a command line, he could call an HTTP endpoint, a webhook, whatsoever. If we look in details at the architecture, how exactly this is working. Basically, today when you execute a container on the machine, you will use a container runtime. Could be Docker, could be Containerd, could be Cryo, could be Podman, could be whatever. And the role of the container engine is to talk to your kernel. On the operating system, you have a kernel, and a container is just a software isolation mechanism that is managed by your container runtime. So whenever you do Docker run to start a container, Docker will actually generate a set of syscall to your kernel to reserve the memory, to open a namespace, to start a series of processes, to reserve a space memory for your network, etc. So whenever you execute a command in Docker, you will actually trigger some syscall through your kernel. So events, you are emitting some tracks. Okay? So what is happening is that Falco is actually listening to the kernel events, and based on a series of rules, will be able to trigger some alerts. So basically, Falco is able to read at what is happening at the kernel level by two strategies. He will either use the kernel module. So a kernel module is a piece of software that you can install directly on your kernel. You need to have privileged accesses. But of course, if you are running in cloud, you don't have access to directly the machine, and you can't really manipulate such deep dive area. So you can also use, another approach is to use eBPF props. eBPF, it's a protocol, it's a technology that allows you to execute just-in-time execution very close to the kernel. It's been very popular since we do some networking analysis, especially Wireshark, for example. It uses BPF. Okay? So Falco is listening to the events that are generated at the kernel level using these two connectors. He will process this event inside the core with two libraries, libsprint and libcap. And basically, with the engine of rules, he will process this event and maybe generate alerts. Of course, we can feed Falco with different inputs. Falco exposes, for example, a web server. And with this web server, we can feed the audit event log coming from Kubernetes. Today, when we operate a Kubernetes cluster, we are able to ship logs to any system we want. Okay, it's a basic API, and we can configure this API to talk to, for example, an endpoint and to ship logs somewhere. It's called audit sync. So whenever an action is executed on Kubernetes, I can store that somewhere outside of Kubernetes, and I can run some tracks, log, and audit. It's very useful when you run production cluster because you can actually analyze the series of steps that leads you to, for example, an incident. So it's useful as well for pure operation perspective. Since last year, the version 0.31, Falco also implemented plugins aspects, which means that you can basically implement your own SDK, and you can also configure your software to ship, for example, events to Falco. And then you can reuse the Falco lists, macros, and rules to actually trigger some extra behavior, which is interesting. So, for example, one of the first connectors that was implemented was to connect to CloudTrail, which is a very famous log AWS managed systems. And basically, you can also ship to Falco some application logs, which is interesting. The way Falco works, as I mentioned, you can deploy it by two ways. If you are familiar with Kubernetes and you want to run Falco inside Kubernetes and benefit from it, you can use a daemon set and you can install it very easily via Helm. If you want to isolate Falco from the underlying cluster he's managing, you can use basically a package manager and just install like a standard binary. The only limitation is that you need to synchronize and orchestrate, of course, the deployments, and you will need to use, for example, a tool like a configuration management tools such as like Ansible, Chef Puppet, whatever. And you will need to make sure that the instance is constantly running. The way we choose to go with one way or another is how much do we want to isolate Falco. Technically, Falco is kind of like monitoring your Kubernetes cluster, which is kind of weird if you also rely on it to run Falco. So some companies, some services, they prefer to isolate these monitoring activities from the cluster they are monitoring. But of course, it generates some overhead in terms of management. In Falco, you have different artifacts, right? Like I mentioned, the rule that I mentioned is really like the configuration, the behavior that you will need to implement to benefit from Falco. You also have macros, which is a reusable configuration, and you have also a series of lists. I will go in details, so you will have what exactly is happening. So like I mentioned, basically, Falco is processing events, okay? So it means that with this event system, you will have to kind of like backwards and reverse what is happening. And for example, here you have the rule of the terminal that executes inside a shell. And basically, you are kind of like defining, okay, based on a series of conditions, this is what is going to happen. I will have an output, meaning a message, that will mention a shell was spawned in a container, and you can add, of course, a series of variables to find which process are we talking about, in which namespaces, which user executes these shell commands. And to do that, you have this condition in which you rely on macros. For example, you have the macro openRead, which is a very low-level macro. For example, here, with this series of conditions, you are defining an event system. And with this set of conditions, you deduct that it's open file. So basically, when you open a file inside a container, you will generate this series of events to the kernel. And Falco is able to read these events. The list is just an aggregation. For example, here we are listing the shell binaries to define that whenever we use shell binaries, the lists, we actually cover everything. Okay? So of course, you don't have to implement everything on your own. Falco already provides a set of like existing rules on different aspects, the file system, the network, the processes. So you can, of course, reuse them instead of having to implement them on your own. Okay, so you can detect if someone is opening a file, if someone is removing a file, if someone is modifying a sensitive file, if there is some outgoing and ingoing communications, if there is some weird processes that are spanning out. So it's kind of like already rich. You can also do that at the application level, of course, with the example that I just mentioned with Elasticsearch. For example, in Elasticsearch, we have a series of like allowed ports, and we also have a series of allowed processes. If suddenly you leave this series of like expected behavior, we are generating an alert, which is of course very interesting. You don't want that someone suddenly run a weird processes inside Elasticsearch. It's just like unexpected, and you would like to be able to detect that. So again, there is a series of rules that already exist at the application level for very famous and already like covered like stacks. So it can be MySQL, Redis, Elasticsearch, Postgres, etc. So you can already reuse this rule and adapt them a little bit depending on your setup. Finally, I can mention in Kubernetes we have the ability to have audit events. Like I mentioned, the audit sync that I just described earlier in the presentation, basically we are emitting this kind of event whenever something is happening on the cluster. In this request, for example, we know that someone is trying to modify, for example, is trying to listing config maps inside a namespaces. With this event, we are able as well to define a series of rules that Falco will understand for Kubernetes. For example, here, we have a series of like allowed namespaces. We define what is the concept of the pod. And we define that, for example, we can create privileged pods only in some specific namespaces. Otherwise, this is not going to work. Okay? So basically, we are able to play at different level, container, application, and Kubernetes level. Now you are wondering yourself, okay, that's nice what you introduced, but how can we like leverage these alerts? Basically, we can broadcast these alerts to various like outputs. If you already have like a monitoring stacks using FluentD, basically you don't have to do much because basically all the alerts will be outputted directly on the container standard output, meaning you are already logging the alerts. So it's not a problem. Most of the like production cluster, they already have this monitoring like stacks with FluentD, Kafka, Elasticsearch, so it's not really a problem. If you don't have that and if you start fresh from new, you can use like Falco Sidekick. It's a very nice open source project, Falco Sidekick, which is a super aggregator of like Falco events. Basically, you have a series of connectors, and you don't have to do anything except configuring a file in Falco Sidekick, and Falco Sidekick will be able to distribute your alerts to various outputs. Could be Kafka, Elasticsearch, Teams, Slack, OpenFast, and Sidekick come also with his own web UI. So it's pretty convenient when we want to connect to very various outputs, the alerts from Falco. Of course, what you would like to do as well is to analyze the alerts and especially understand what is happening. And you can do that with a standard stack like Elasticsearch and Kibana. And you can generate some very nice dashboards to, for example, review what kind of alerts do we have, in which namespaces do we have these alerts, what kind of processes is generating these alerts, and you can continuously like monitor what is happening and work closely with your team to reduce the alerts and identify false positives. So it's very important to implement that from the beginning, especially when you have like big cluster. What exactly we can do? Of course, we can analyze in the space, in the time, in the level and the criticity. For example, I would like to understand in which namespaces, in which pods, what kind of user is generating these alerts. When does it happen? Do we have a specific hours? Do we have a specific time periods when it's happening? And do we have any correlation between like these alerts? I would like as well to have different levels. Is it mostly container? Is it Kubernetes? And then I can work with the teams to actually improve that. To go a little bit further, this is something that we have implemented. It's pretty nice. We would like that as a response to, for example, an alert, we don't have someone that needs to manually act, but we have a process that is able to react dynamically. So here, for example, we would like to do that whenever someone is executing inside a container, we would like to put this container in a quarantine. We would like to make sure that this container becomes unreachable. To do that, we rely on a stack that is called Argo event. This is the small icon here. And Argo event is able, for example, to trigger some processing against the cluster Kubernetes, against the API. So for example, what is happening? Falco is listening that a shell has been executed inside a container. He will talk to Argo event stack. And in Argo event stack, we have defined a workflow. And whenever this alert is received, what are we doing? We are triggering actually two operations. First, we will label the container that has generated this alert. We are just basically patching it. We are doing a patch request HTTP to the API server. And we assign a specific label to this container called suspicious activity. And secondly, what we are doing is that we create a network policy that isolates completely the network of this specific container. So we have like this scenario, and of course we would like to have different escalation level. But basically it's working pretty fine. It means that when something weird is happening, we can isolate the container, even temporarily, and do some like manual effort later. But we can already like restrict a little bit the impact in case something weird is happening. In case you would like to adopt Falco in your security strategy, this is like a recommended approach. The very first step would be probably to start looking at what you have in terms of like Kubernetes. What kind of version do you have? What kind of package? Do you already have a lot of like privileged pods? Do you have already a lot of containers that are running as root? It's very important at the beginning to try to understand the context of your cluster. It's even more true because today we have like Kubernetes clusters that are very like legacy. And sometimes we are a little bit surprised when we arrive and we open what is happening. So try first to analyze what's going on. Secondly, you will deploy Falco, of course, and you will need to communicate with your team. Because it's important that they realize what is happening and that they are aware that suddenly some alerts will be triggered, and of course they need to react consequently. The second step would be to analyze the result and to organize a series of workshops with your developers. Guys, we have identified that there is a wrong configuration of the Redis container that you are using. Can we work together? How can we reduce the privilege on this container? How can we work together to improve the rules? The idea is really to involve the development teams to restrict a little bit the context in which Falco is operating and to be relevant on the alerts, because at the beginning you will have a lot of like alerts generated. And at the end you will have this enforcement process. Based on the alerts that you have identified, you will enrich your prevention and your defensive measure. Because you have detected a weird behavior that is happening, you can now generate new rules, new airbag rules, for example. So you can enrich the prevention with the detection aspect and run a continuous improvement loop based on that. For example, you have noticed that one Elasticsearch container is doing something weird. You managed to fix the solution. And based on this delta and alert that you have introduced, you can like harden the container so it will not be able to execute this weird behavior anymore. So you can rely on the standard approach of network policy, pod security and mission airbag to actually leverage this alert from Falco, which is very positive. So basically, now that we have like a good detection engine, we are able to continuously enrich and improve the prevention measure. Couple of limitations based on our experience with Falco. From the beginning, you will have a lot of alerts that will be triggered. So basically, if you have already a Kubernetes cluster and you just like install Falco, then be prepared, be ready, because you will receive a lot of alerts. The second issue that we got is that technically we can cheat a little bit Falco. It's a very advanced hacking scenario, but basically Falco is processing events inside a ring buffer. So basically we have a buffer that is very close to the kernel, and if of course you manage to generate a huge amount of events, some events might be dropped by Falco. So the community is aware of that. They have introduced different mechanisms, but be aware that if suddenly you have a lot of events that are generated, some might be like excluded from Falco. You also have some issues if you are managing very, very big cluster, above 400 nodes. For the same reason, the buffer hits some limitation and the correlation between the nodes is kind of like challenge. The third limitation as well is that whenever you upgrade your cluster, and especially the kernel of your machine, you need to be aware if this is compatible with Falco. Why? Because Falco is listening to event system. If suddenly running a containers generates some different calls, the rules won't work anymore. So it means that you need to constantly take a look at the way you are evolving and upgrading your Kubernetes clusters toward Falco. So most of the time, Falco is very ahead, so it's not really a problem, but this is something we need to pay attention at. A couple of recommendations that are quite obvious. At the beginning, you will probably need to restrict the number of elements you want to watch, maybe specific namespaces, maybe specific containers. You might also be tempted to drop some rules to start with something that you can master, which makes sense as well. I would highly recommend as well to structure a pipeline to collect and store alerts from the beginning. So basically having Elasticsearch Kibana from the beginning, this is highly advised to understand what's going on and to already generate value from these alerts. Finally, you need to reuse absolutely the existing rules because otherwise you will have some issues from the beginning. These are the core recommendations. So thank you very much for your attention, and I will be very happy to answer any question you have. Sorry, can you repeat the question? Yes, so okay, it's a very good question. So the question is like, where do we install Falco? Is it on the cluster? Is it on the nodes? And what is basically the conception in terms of resource? Is there any overhead? So I will come back to the slides just to re-explain this part. We have the ability to install Falco at two different levels. Either we manually install that on every node of the cluster, but it's running as a binary, so it's outside of any Kubernetes context, or we can run Falco as a container inside the Kubernetes cluster, and we will use a daemon set. A daemon set is just like a Kubernetes abstraction to make sure we have, whenever we create a node, automatically the container deployed. The overhead is not super huge. For example, it will add 10 to 15% in terms of overhead, maybe less, even 5 to 15%, depending on the size of the cluster. So it's not really consequence, especially because it's been implemented with like very low-level stuffs, so basically C++ Golang, and you are only like listening to kernel events. So it's not that a huge overhead. Any other question? No question. Thank you very much for your attention. And if you want to have a coffee, we can discuss later. Thank you.
Thank you for the session, and here's a small token of memento.